Welcome. In this video, I'm going to try to introduce you to some of the key ideas or concepts behind organic chemistry. Organic chemistry is this whole branch of chemistry, so to think that we're going to cover organic chemistry in one chapter is more than a little ambitious, but we're going to see if we can get you to understand some of the big concepts and overlying concepts that really carry throughout the whole branch of organic chemistry. So, what kinds of chemicals are included in organic chemistry? All biological molecules, and that's whether it's a plant or an animal, a bacteria. So anything from simple sugars to DNA are considered biological molecules and are organic substances. Any fossil fuel, because remember they come from formerly living things, so gasoline, oil, natural gas, propane, all those things, coal, those are all organic compounds. Nearly all synthetic materials, which most of our clothing is actually made at least partially from synthetic material. Things like nylon, polyester, lycra, spandex, Gore-Tex, those things are all synthetic. Other than cotton, wool, and silk, we don't wear a ton of natural fibers. And then many products that you use day to day, paint, detergent, all the plastics out there, pharmaceuticals, a lot of them contain organic substances, makeup, all of those things. So what defines it as organic? An organic compound is defined as any molecule containing carbon. And in nearly all cases, it's also going to contain hydrogen. There's a whole class of compounds that contain only hydrogen and carbon called hydrocarbons. But many times there's also oxygen, nitrogen, chlorine, or sulfur involved. So not just hydrocarbons, big category. So part of the reason organic chemistry is such a big branch is because carbon has 4 bonding sites. So it can make an endless number of molecules with things extending in 4 different directions. So carbon is known to form more compounds than all the other elements put together, which is a pretty amazing number when there's over 10 million different compounds out there. So again, its unique ability to form 4 bonds and to form either long chains in multiple directions or even form rings with itself is what makes carbon substances so ubiquitous, so commonplace out there. And this unique trait actually gets a name called catenation. And because there's so many compounds out there, it needs a classification system. So organic compounds are classified into families, or also known as homologous series. And these families are closely related to each other, hence the name family. And it's all based off this functional group they have in common. And it's called a functional group because this group determines how the organic molecule is going to function or react. Okay, it's the reactive part in determining the chemical behavior. And then there's a less reactive part known as the hydrocarbon skeleton or the carbon backbone or the stem, or it's simply abbreviated as the R group. So for example, if you look at ethanol, its condensed structural formula is CH3, CH2, CH2OH. And I'm just going to take a minute and draw it out here as to what it would look like. So the condensed structural formula is telling me how to draw it, a C with 3 H's bonded to it, and hydrogen always has to single bond, so that helps. Then another carbon with 2 H's, another carbon with 2 H's, and you'll quickly realize that a CH3 group is letting you know it's on the end, whereas a CH2 group is an inner carbon, and then an OH at the end. So that's ethanol. And the OH at the end, this is the functional group known as a hydroxyl group, and that identifies it as part of the alcohol family. And then this group here is my hydrocarbon or my R group, and it's 3 carbons long, which lets me know it's part of the propyl group. So any organic compound you look at, you should quickly be able to pick out the functional group and the hydrocarbon chain. So a family or homologous series has certain features in common. Obviously, they all have the same functional group. So that means they can be represented by the same general formula. Successive members are going to vary just by a CH2. You're just adding one more carbon to the backbone. And as I said, a good thing to learn quickly in organic chemistry is that a CH3 group indicates it's an end. Could be the end of the long hydrocarbon chain, or it could be the end of a branch, whereas a CH2 is an inner carbon group. And then number 4, members show a gradation. That's just a fancy word for increase in physical properties like boiling point density and viscosity due to the increased van der Waals forces. And then members have similar chemical properties, which is why we call them a family. So again, the 2 parts of every organic molecule are the functional group and the carbon backbone, and they each play a different role in the properties. The functional group determines the chemical behavior or the functioning of that particular compound. The carbon backbone is going to impact the physical properties. So looking at the physical properties first, why does a bigger or longer backbone affect the physical properties? Well, think about it like spaghetti noodles. If you have shell noodles versus long spaghetti noodles, you've got a lot more surface area between 2 spaghetti noodles than you do between 2 little shells or little rings. So that allows more temporary dipoles to form. So even though there's still not any permanent dipoles, the chances of a temporary dipole are much greater when you have this long structure in contact with another long structure. So the increased attraction, or intermolecular forces, is going to increase the density, increase the viscosity, and increase the boiling point. The backbone also has an effect on the molecule's overall polarity, but now it's going to have the opposite effect because the backbone will be nonpolar. Since carbon and hydrogen bonds are only slightly polar and the backbone is symmetrical, overall the backbone portion of any organic molecule is nonpolar. And if the functional group is polar like OH, then that end of the molecule is going to be polar, but the other end is going to be nonpolar. So if you have a very short backbone with a polar OH, that OH has a strong effect on the molecule. But if you have a long carbon chain with just an OH end, then it's kind of more like an iceberg. The polar end is just the little bit we see, whereas there's this huge, long, nonpolar part also influencing the properties. So polarity generally decreases with the increasing length of the backbone. So here's a table down below just showing you with a family called the alkanes, and you might recognize some of these names like methane, propane, butane, octane. But as the chain gets bigger, the boiling point definitely increases. And in fact, the first 4 members are gases at room temperature, and by the time you get to pentane, the intermolecular forces have increased enough that now we have liquids. So this family, the alkanes, are mostly what we think of as the fossil fuels. And this is a big deal that the boiling points vary so nicely because this is how oil refineries separate the different kind of fuels into like groups. They simply boil it off. Those big, huge distillation towers you see, they're boiling it off and collecting things at their different boiling points. Chemical properties, then, are determined by the functional group. And so, really, you need to memorize the different functional groups. And I took a screenshot here of page 314, and I suggest you maybe do the same thing and keep it nearby or even print out a copy of it. But I will go through a video a little bit later trying to give you some hints on how you remember the difference between an alcohol and an aldehyde and a ketone and a carboxylic acid. Lots of names, but actually when you look at what's going on, it's really a difference between a single or double bonded oxygen and oxygen with or without a hydrogen. And there's just very simple nuances to the differences in the functional groups. The key is because there's so much similarity among the functional groups, you can easily change an alcohol to a carboxylic acid. And so we're able to change one functional group to another or change one organic compound to another quite easily, which allows us to make ethanol blended gasolines and make them function quite well. So organic chemistry, a whole new category, lots of exciting stuff, and we're just going to scratch the surface of it.